Hello students, welcome to the physics session. In today's session, we will be discussing Biot-Savart law applications and a few numericals. Applications, especially magnetic field due to circular loop, and a few numericals based on state current carrying conductor as well. Okay, it is meet at 8:30. Right. Okay, everyone. Yes, welcome back to the physics session. Right. Open your physics books. Right. Okay. Yes, guys. Yes, come fast, come fast. Open your physics books, everyone. So, right, in the previous class, we have discussed about what is that magnetic field due to straight current carrying conductor, right? And did we discuss the applications? Infinite conductor, semi-infinite conductor, current carrying conductor, and semi-infinite current carrying conductor, and finite current carrying conductor, etc. Then we'll see once again magnetic field due to a circular current carrying wire at the center, and then we'll discuss few numericals based on this. Right? So let us try to write down once again the expression for general expression for magnetic field due to straight current carrying conductor. So B is equal to what? Due to straight current carrying conductor. Sorry. So magnetic field due to straight current carrying conductor. We have a current carrying conductor, which current I is flowing at a point P, which is at a distance D. What is the expression for magnetic field? B is equal to mu naught I by 4 pi D into sine alpha plus sine beta, where alpha is angle made by the line drawn from the top end to the point from the perpendicular line, and beta is the angle made by the line drawn from the bottom end from the perpendicular line will be beta. This sign conventions you have to follow carefully. So usually the angles will be measured with respect to this perpendicular line. So the angle measured above positive, below negative. Got it? Right. This point we have to make use while doing some numericals. Now let us see the special cases. Special special cases. First one is magnetic field at any point on the axis of a current carrying conductor. Magnetic field B at any point on the axis of a current carrying of conductor. So if the point is somewhere here on this axis or along the length also can consider, then you have to consider small element. So for this current element, the direction will be in the direction of current, and the position vector of the point will be r vector. This dl vector and r vector will be parallel to one another. From Biot-Savart law, the angle between them is 0. So b dv equal to 0, and hence b is equal to 0 for this point. This already I have discussed. Right. Next, the another special case is magnetic field due to an infinite conductor. B due to an infinite conductor, infinite thin current carrying conductor. That is also important. Thick conductor means again the scenario will changes. So we have to consider a conductor, current carrying conductor in which current I is flowing from bottom to top. So it is an infinite conductor, means this end is going to infinity, this end is also going to infinity. So due to this current carrying conductor at a point P going to infinity, this line almost becomes parallel to this conductor. So it will look like this conductor, I mean line. So the alpha will become 90 degrees. This was for infinite conductor. Whereas the line drawn from bottom point to this point, it is also going to infinity. If the length is increasing, line will go like this. Where the length is going increasing, so beta will be increasing gradually. If it is infinity, almost it looks like parallel to the conductor, or you can say anti-parallel. So this will be in this direction. So this will be beta. From with respect to this, beta will be equal to 90 degrees. So magnetic field is due to this conductor. What is this conductor? Infinite conductor is mu naught I by 4 pi. The perpendicular distance of the conductor from the point is d into sine alpha plus sine beta. Alpha is 90, beta is 90. So sine 90 plus sine 90. Sine 90 is 1 plus 1, 2. So you get into 2. So we can write this further as 2 into 2. If you cancel, then you get b is equal to mu naught I by 2 pi d. This is the magnetic field due to infinite current carrying. The next one is third case, magnetic field due to semi-infinite conductor. Semi-infinite. B due to semi-infinite semi-infinite conductor. Semi-infinite conductor. Or this is it gives same meaning. If the question is what is the magnetic field due to infinite conductor near one end, or magnetic field near one end of an infinite conductor. Magnetic field near one end of an infinite conductor. So that can be understand like this. If you have a conductor, in this current I is flowing, so if this is going to infinity, but you are near one end. So this is same as semi-infinite conductor, where you can call this conductor as semi-infinite. So for this conductor, for this kind of conductor, if we consider a point somewhere here near this end, if we draw a perpendicular line whose distance of the point from the conductor is d, then by using the same logic, this because of infinite length, alpha will become 90 degrees, but beta. So as this length is decreasing, or beta will be decreasing gradually, as these two are coinciding, beta will become 0 here. Beta becomes 0. Right? So what happens to the magnetic field? B is equal to mu naught I by 4 pi d into sin alpha plus sin beta. Alpha is 90, beta is 0. Sin 90 plus 0 is 1 plus 0 is into 1. So this is the magnetic field due to, into 1 is this only. Is the magnetic field due to semi-infinite conductor. Is it clear, everyone? Right. Whereas if we come across a conductor having finite length, then we how to find the magnetic field at a point due to finite conductor, or magnetic field due to a conductor having finite length. What is this? Fourth case. Due to a finite conductor. Due to a finite conductor. So let us consider this is a current carrying conductor provided here you have to follow 2 points. The conductor will be having finite length. Let us say length of the conductor is L, and magnetic field due to this finite conductor at a point which is bisecting, or if the point is on perpendicular bisector, it is bisecting the length, or it is on perpendicular bisector, means you have to draw a line from the midpoint, perpendicular line at the midpoint, and at a point P, which is at a distance D. Then what is the magnetic field? You are asked to find. You have to say this length will be exactly half of this. This will be exactly half of this. Is it clear? So if it is a perpendicular bisector, we can say if it is having a particular length. If you draw one line here, L, then so this two are having same length. If you draw a line like this, because of this, what do you call it? A perpendicular bisecting condition, this angle will become pi by 2. This looks like a square or rectangle, right? So depending on this distance, rectangle. So this angle will be pi by 2, or you can say alpha is equal to not pi by 2, pi by 4, 45 degrees. Pi by 4 radians are 45 degrees. Is it clear, everyone? 45 degrees. And similarly, this also will be, what is this? Beta. This is alpha and this is beta. Beta is also equal to 45 degrees. Is that point clear? So, by making use of this, how to find the magnetic field here due to this entire conductor? By using same formula. What is that? B is equal to mu naught I by 4 pi D into, what is this? D. What is this D? This is D. And into sin alpha plus sin beta. So what is sin alpha plus sin beta? Alpha is 45, beta is 45. Alpha equal to beta. Both are equal angles. So sin alpha plus sin alpha, 2 sin alpha or 2 sin beta. Any term we can take. 2 sin alpha, that is nothing but 45. 2 sin 45. Sin 45 plus sin 45 is how much? 2 sin 45. Is it clear? So if it is other than 45, then so that angle you have to disturb. If it is the angle bisection, provided the angle is different from this, but if both are equal, then you have to consider accordingly that angle. So here it is sin 45, 2 sin 45. So what is sin 45 value? Right? Or if let us consider this is not exactly equal to 45, but these two are these on by what do you call bisecting. That 45 you can consider special case value in the numerical. In a general case, this is some alpha. This is a because it is a bisecting perpendicular bisector, or you can say it is a this perpendicular bisecting means this will the angle will be angle also will be bisecting. This point is called as the angle bisector. So that means though both of these angles will be equal. That means alpha is equal to beta. Alpha is equal to beta, general case methods. So in this case, as alpha equal to beta, we can take sin alpha plus sin beta is 2 sin alpha or 2 sin beta. What is sin alpha? Opposite side by what? Hypotenuse. If you say this is distance of the element from the point is R, then from this you can take this is O, P, Q. If you mark it as, it looks like a right angle triangle, then R will be equal to square root of D square plus L by 2 square is L square by 4. On simplifying this further, and right we'll get 4d square plus L square by 4 under root. So root by under root by 4 becomes 2. So you can write that as what is this? This one. But do we need this? Yes, here you can write this mu naught I by 4 pi into 1 by d, or by d, we take d as this, then 2 into sin alpha can be taken as what is this? Opposite side by hypotenuse, that is L by 2 by r, small r. So here 2 can get cancelled. We can keep as is in the numericals. The r value is given. If not, further you can write it as mu naught I by 4 pi d into L by r is nothing but square root of d square plus L square by 4, or 4d square plus L square by root 4 becomes 2. The 2 can bring here and we can write 2. This will be the magnetic field due to this kind of function. Is it clear? Right? These are few simple special cases of magnetic field due to what? Magnetic field due to state current carrying conductor. Infinite conductor, semi-infinite conductor, finite conductor. By doing numericals, if at all it is given that a long straight conductor is there, but if the length is not mentioned, you have to consider that conductor to be an infinite conductor. If it is mentioned, then that particular length will be. Okay, right. Now let us see quickly for one set of students we have discussed, for others are not. So let us see quickly. Magnetic field due to circular current carrying wire at the center. Then we'll try to work out the questions based on the combination of both. Next, write down magnetic field, magnetic field, magnetic field at the center of circular arc. Magnetic field actually it's an arc of a circle. Or it is circular arc which is not complete circle. You can read things as magnetic field at the center of center of a circle. Or you can say magnetic field at the center at point O, which is the center of the circle, but we are not considering the entire circle. So that the sentence formation have to take properly. Okay. How can you take sentence? Here you can, according to your own sentence formation, you can take. So otherwise, you can say magnetic field B due to an arc of a circle, comma, at O, magnetic field due to an arc of a circle. Let us consider there is a circle of center O, and this is radius R, and in this we are considering only one arc, a particular arc. This is arc AB, arc AB or AB, either we can take it. So in this current I is flowing, current I is flowing from B to A, current I is flowing from B to A. Due to this, to find the magnetic field here, and it is also given that this arc is subtending an angle theta at the center, it is having radius r. So to find the magnetic field, we have to consider a small element of length dl, and we have to draw a line from the element to the center, and we have to apply Biot-Savart law. According to Biot-Savart law, dB is equal to mu naught by 4 pi into I dl, length of the small element into current through that element, by distance square, that is r square, distance between the element and the point, that is radius square, into sin theta. Sin theta is angle between this element and this line. These two will be perpendicular to one another. So 90. So 90 is what will get ideal by r square. That is a small field due to this. Which is the entire arc whose length is, if you consider the total length of this arc is L. Due to this arc, if you want the magnetic field, you have to integrate it. D is equal to integral of dB. Integral of dB is equal to mu naught I by 4 pi r square into integral of dl, you can take, where dl is nothing much the this length totally. So you can say where the length goes from, where the starting point is ending point goes from 0 to L. So integral of dl is L. If you apply the limits, you will get L only. So you will get B is equal to mu naught I by 4 pi r square into L. But if the angle and radius are given, then this L can be taken as, by using the relation arc is equal to r, so the angle is equal to angle, theta is equal to arc length L by radius r. So theta is equal to L by r. From this you can say L is equal to r theta. Substitute this here, then you'll get mu naught I by 4 pi r square into r theta. On simplifying this, one r gets cancelled here. Then you'll get it is mu naught I by 4 pi r into theta is magnetic field arc due to the arc of a circle at the center. Due to arc of a circle at the center of the circle is this. If this theta is pi by 2, you have to take accordingly. That means if you consider semicircle, angle subtending by semicircle at the center will be pi radians. If you consider the entire circle, And angle subtending by the entire circle of the center should be 2 pi radians. According to this, we have to find the magnetic field due to circle at the center, semicircle at the center, or due to any arc which is subtending an angle of 30 degrees or 60 degrees, etc. also verified. Okay. So by making use of this, now let us do two questions. Okay. So open your volumes. Nine. We have half an hour. Right. Let us see one simple question based on this exactly this one now. Level 2, exercise 2. Yes, ma'am. Look into the books. Level 2, exercise 2. We'll see few questions in level 1 and few questions in level 2 only based on these concepts. Okay? Only based on these concepts. Level 2, exercise 2 will be, this is the figure. We have a circle. We have a circle in this. So you have center O and radius. Let us say this is radius R, small r. It is mentioned that in this we have considered R. This is removed. This part of this is removed, and a current is entering in this along a wire connected here, and it is passing like this along this part, remaining part, and it is leaving along this. Are you following this? Yes. So this current I is entered and leaving here. So that this angle of this part is 90 degrees. This is radius. This is the point of P. It is mentioned as center of the circle is P. What is the magnetic field due to this point center the point P? So how to do this? To work out this, let us consider that it is not mentioned from where current is coming. Let us consider this Z is an infinite conductor. This is also infinite conductor. It is going in an infinite conductor. Okay. Now let us divide this into three parts. This is part one. This third part is part two. This is third part. So the total field at P is proper limit. The total field at P total field at P is equal to field due to the first one plus field due to the second one plus field due to third conductor. If you observe here carefully, the point P is lying on the axis of the first conductor. So what is the magnetic field due to any current, straight current carrying conductor at any point on the axis or along the line? What is the magnetic field due to straight current carrying conductor at any point on the axis? On the axis. Why? Theta equal to 0. Right? So here this point is lying along the axis of this conductor, and this point is lying on the axis of this conductor also. So B1 and B3 or 1 and 3 will not contribute any magnetic field. B1 equal to B3 equal to 0. Is it clear everyone? Here B1 is equal to B3 is equal to 0. And what about B2? B2. It is a circular part. So it is given that this angle is 90, but the magnetic field is given by this conductor. How much angle that conductor is subtending there? That should be that is what we have to consider here. So we know in general magnetic field due to arc of a circle is given by mu naught I by 4 pi 4 pi. What is this? 4 pi r. You can consider this is r or d or whatever it is. Circle, right? It's radius. 4 pi r into theta is general formula. What is the angle subtending by that part? Total angle subtending by the circle the center should be 2 pi radians or 360 degrees. So 360 degree in this 360 subtract 90 that much angle it is subtending here. That is nothing. This is nothing but 360 minus 90. How much? 270 degrees it is subtending. 270 only. Yes. So it is in terms of radians. If you observe the options are given in terms of numerical values are given here. Current is given. Now here current is given as how much? 40 amps and radius is taken as how much? 3.14 centimeter. So this you have to write in SI units. 3.14 into 10 power minus 2 meters. You have to convert all into SI units only. So don't do this mistakes while doing the numerical. So if you substitute it here, then what will you get? So to find the value in SI units, angle always should be in radian. Angle always should be in radians. Degree is not SI unit. Radian should be the SI unit. Okay. So 270 degrees, or you can write it as what is this theta here? Theta is equal to 2 pi radian minus 90 degrees is pi by 2 radian. How much is this? 4 minus 2, 4 minus 1, 3, 3 pi by 2, or 3 by 2 pi is theta. Is it clear, everyone? Yes, substitute this here, then you'll get mu naught by 4 pi. The value you have to remember. What is this? 10 power minus 7. I is how much? 40 ampere by R. R is how much? 3.14. 3.14. What is this? Centimeters. So 10 power minus 2 meters. 2 meters. Right. Then what else is given here? Theta. Theta is 3 pi by 2. Here pi value is, again you can write it as 3.14. So 3.14, 3.14 will get cancelled. Right? And simplify further. And this is 2, how much? 20. 20 into 3 here, 10 power minus 2, minus 5, here cancel, you get minus 5 remains. So the 20 into 3, how much? 60 into 10 power minus 5. So options based on options, again you have to simplify. So the options are given in terms of 60 or something else. The 60 into 10 to the power minus 5. What is magnetic field? Tesla. But they are given in terms of 10 power 3 and 10 power 4. So you can write it as V is equal to 6 into 10 to the power minus 4 Tesla. Is it clear? Right? Yes. Next one. Any confusion? 4 pi. Where? This 4 pi. What I have mentioned here, bracket. V naught by 4 pi. Value should be 10 power minus 7. That is a constant, right? But you have taken as 10 power minus 7. So here we can write otherwise because V naught by 4 pi is 10 power minus 7. Okay? Right. So next, question number 5. Let us see question number 5 quickly. Question number 5. Level 2, exercise 2. Level 2, exercise 2, question number 5. So what is given here and what you are asked to find? See, the magnetic field at the center of semicircle, at the center O of semicircle in the figure, at the center of semicircle O in the figure, in this formation, so you have to understand it properly. Okay, there is some printing mistakes there. Okay, right. So the figure you have to draw. So you have to draw this figure. It is given that there is a semicircle. This is a semicircle, and this is the diameter of the semicircle, right? And this is center of the circle, O, and its radius is given as R. At this point, a straight conductor means the conductor is connected. In this current I is flowing here. So whenever you consider this conductor is given means you have to understand that current is coming from somewhere. That somewhere you have to take it as infinity. Okay? Its length is not mentioned. Then this conductor will flow in this further, and here again it is connected to another straight conductor. This current I flows. So where it flows, it will be going to infinity. So I have to consider this conductor as semi-infinite conductors. This is one semi-infinite conductor, this is another semi-infinite conductor, this is circular conductor. So, what the question is, the magnetic field at the center of semicircle O. What is total field at O is the question. So, total field due to this, how much? Due to this, how much? Due to this, how much? I will take this as 1, conductor 2, conductor 3. So total field B at O is equal to B due to 1 plus B due to 2 plus B due to 3. Got it? So what is this? Try to first observe the directions in this kind of cases. Try to observe the directions of fields. Then try to get the total field. Some cases the field will be cancelled. Some cases they may add up. Okay. You see here, this is a conductor, semi-infinite conductor. Due to this, field here will be in what direction? The current is going in this direction. To find the current magnetic field direction, we have to stretch the current in the direction of current, stretch the fingers onto the point. The field will be out. In this, current is moving to the right. So stretch the thumb in the direction of the right, stretch the fingers on the point. Palm direction is outward. The field will be out. So due to both of these conductors, field is out, they will add up. So both are similar kind of conductors. So same field they will contribute. So you can say B1 equal to B3. So you can say do B1 after B3. Then what is the magnetic field to the circle? I mean, what direction is acting? So if you observe this, thumb wheel will be outward only. So all are outwards, they will add up in same direction. So no need to worry about the directions. So you can directly can take this is equal to 2b1 plus b2. So what is b1 here and what is b2? B1 is equal to magnetic field due to semi-inverse conductor. You have to remember that formula. So here alpha equal to 90, beta equal to 0. So what is the general formula for magnetic field due to straight current carrying conductor? Mu naught I by 4 pi d into sin alpha plus sin beta, right? For semi-infinite alpha is 90, beta is 0, so you get 1. So mu naught I by 4 pi d. Here, that d is perpendicular distance is small r, so you can take this is equal to mu naught I by 4 pi r, B1 and B2. What is B2? Magnetic field due to semicircle at the center. In general, magnetic field due to any arc is mu naught I by 4 pi r into theta. Here theta due to semicircle is nothing but pi radians. Substitute here pi cancel again mu naught I by 4r. So it is mu naught I by 4r. That's it. The radius is smaller. So this if you substitute here, you get total field. It is equal to 2 mu naught I by 4 pi r plus mu naught I by 4r. Here mu naught I by 4r is common. You can take this out and simplify based on the options. If options are given as it is, you can leave as it is. If options are given little different, based on the options, you have to simplify. So look at the options, right? They have given in terms of mu naught I by 4r, they have taken common. So mu naught I by 4r we take common, we not by 4r out, 1 remains here. 4r out, 5 is there. You can write it as 2 is there. So 2, this you can write it as 2 plus pi, 2 plus pi by by this pi will come here. So it is equal to, can also write this as mu naught I by 4 pi r into 2 plus pi. 2 plus pi all divided by pi. That pi you can write here. So it becomes mu naught I by 4 pi r. So option 4 is the right one. Okay? Yes? Yes? Right. Now I will give few simple questions. Let us see few questions in exercise 1, level 1, exercise 2. Level 1, exercise 2. Level 1, exercise 2. Number 4. Question number 4. The question is, a long straight wire carries an electric current of 2 ampere. The magnetic induction at the perpendicular distance of 5 meters from the wire is given mu naught equal to 4 pi into 10 power minus 7 Henry per meter. Yes. Do this everyone. It's a direct question. So a long straight wire carries an electric current of I is equal to how much? 2 ampere. 2 ampere. The magnetic induction of the perpendicular distance D is equal to 5 meter from the wire is given mu naught is equal to 4 pi into 10 to the power minus 7 Henry per meter. What is the magnetic field at a point which is at the perpendicular distance is the question. A long straight wire means you have to consider this as Yes. Is it clear, everyone? So, long straight wire means you have to consider this as infinite. If length is not given, the current I is flowing. So, due to this, at a point P, which is at a perpendicular distance of D, what is the field here? What is field here? You are asked to find. So, you have to remember direct formula for infinite conductor, or let's apply alpha equal to beta equal to 90, and you remember the general formula. What is general formula? What is the general formula for magnetic field due to straight current carrying conductor? Yes, everyone. What is general formula for magnetic field due to straight current carrying conductor? Open your mouths. Yes, stop doing and give me the answer. Then you can try yourself. Tell me what is magnetic field due to straight current carrying conductor? Everyone. B is equal to mu naught I by 4 pi D into sin alpha plus sin beta, sin alpha plus sin beta. So what is magnetic field due to, in general, straight current carrying conductor is this. Yes, now repeat with me. What is magnetic field due to the straight current carrying conductor? Once again, loudly. I am not getting anything at all. Everyone. Once again. Once again. Last class itself, I made you guys to repeat this 5 times. Still you forgot. Hmm? So what is magnetic field to straight current carrying conductor? Once again. Right. So this you have to remember. Then you have to go to the special cases. So in this case, so you have to remember substitute alpha beta is 90 and 90. D is given, I is given, mu naught is given. Numerical values are substitute and simplify. Let's do it. D is equal to mu naught. You can take here, don't need to take mu naught here, of course, then you can cancel out. Otherwise, you can directly take this value also. 10 to the power minus 7 into I is 2, D is 5. All are in SI units or all are in SI. So, you can take the values as it is into sin 90 plus sin 90. 1 plus 1 is 2 into 2. So, it is how much? Options. Yes. Which option is right? Which option is right? So what is this? 2 into 2, 4. 2 into 2, 4. 1 by 5 is? 1 by 5 is how much? 1 by 5. 0.2. So it is 0.2 into 4 into 10 to the power minus 7. So you can write it as 0.8. 2 into 10 power minus 7 or 8 into 10 to the power minus 8. Yes, this is B, Tesla. 0.8 into 10 power minus 7 Tesla or 8 into 10 power minus 8 Tesla. So simplification part, you have to be careful. So which option is right? Yes. You are having the books or not? Right. Next question number 5. Question number 5. Yes, do it. Do it. Hmm. Don't have to. Hmm. Hmm. You have to come with books during the class. Right? Okay. Yes, let me read the question, note down the data, and try yourself. Note down the data. It is given that a current of 2 ampere is how much? 2 ampere. Write down. I is equal to 2 ampere. Right. Question number 5. The current of I is equal to 2 ampere is flowing through a circular coil of radius 10 centimeter. What coil it is not circular? The circular coil of radius how much? 10 centimeter. Immediately convert into a second. What is this? 10 into 10 to the power minus 2 meters. Then, okay, and it is containing 100 turns. Number of turns n is equal to 100. Okay. Then the magnetic flux density at the center of the coil is magnetic flux density is nothing but magnetic field. Magnetic flux density, magnetic field intensity, and magnetic field strength. All are same. So what is this magnetic field at the center of the circle? We have a circular coil, center O, radius is how much? Capital R. It is having how many turns? N number of turns. N is equal to 100. 100 turns. If you are having a coil of 1 turn, due to that, magnetic field at the center is given as due to 1 turn. What is that? General formula. Mu naught I by 4 pi into theta. 4 pi r into theta. Due to one circular coil of having 1 turn, the theta should be 2 pi. So if you substitute 2 pi, you'll get what? Mu naught I by 2r. This is the magnetic field at the center of the circular coil of 1 turn. Okay, for that the same point, due to 1 turn, due to n number of turns, it is what? N into mu naught I by 2r. That's it. That's it. Substitute the values and find out. Hmm. Got it? Yes. How many got the answer? Have you copied the values, formula, substitute? Right? So it is equal to what? N is 100 mu naught. Mu naught value is also given in the question, right? Hmm? Hmm. Magnetic flux density at the center. We not have to take it as 4 pi into 10 to the power minus 7 or 4 into directly I am substituting. So 4 into pi is 3.14 into 10 to the power minus 7 into I. I is how much? 2 ampere by 2 into R. R is how much? Radius. 10 into 10 to the power minus 2 or 10 power minus 1 also you can take directly. Right. Substitute this right now. Substitute and simplify. Wait, man. Finished? Yes. That's right, boys. Finished? Hmm? 1 0. Cancel here. 10 power minus 2. Here cancel becomes 10 power minus 5. So we have 4 into 3.14. That's it. 10 power something. So by looking at the options directly you can take it right. What is this? 4 fours 16. 1. 4 ones 4. 1 5. 4 threes 12. So what is this? Two decimals. 12.56 into 10 to the power minus 5 here 1. 10 power plus 1. So it becomes 10 power minus 4. Yes or no? So 12.10 power minus 4 or if you put one decimal here 1.256 into 10 power minus 3 or 0.1256 into 10 power minus 2. Yes? Yes or no? Check it out. Question number 5. Right. So you can write this. It is given in the options that 0.1256 into 10 to the power minus 2. What is this? B. Tesla. We have given this one. Right? You should understand how to display the decimals, how to change the decimals. So be careful. Some of the students are doing mistake in like changing the decimals also. Okay. Next, question number 6. See question number 6. Read fast, quickly. Yes. What is the problem? Question number 6. What is the answer for this? Do it yourself. I don't do it. I want the answer from you guys only. Let's do it. Do it. Question number 6. Without books, if anyone comes, hmm, during class time also, keep that in mind. Don't come without books to the classroom. Okay? They are all very good students. Yes? Come with books. Yes? Yes? Come with books. Next. Question number 6. Listen. The question is the coil of radius 5 meter. What is the radius? 5 meter and 100 tons carries a current of 3 ampere. The magnetic induction at a point on the axis. This we didn't do it still. We have discussed that. So what is the magnetic field on the axis of a circular coil path? We have discussed. So we'll do that later. Okay. Next question number 7. Question number 7. Right. Stop it. The question is two coils A and B having the radii in the ratio 1 is to 2, carrying currents in the ratio 5 is to 1, and have the number of turns in the ratio 1 is to 5. The ratio of magnetic inductions at their centers is. The ratio of magnetic inductions at the centers. Two coils are given. Find out magnetic field at the center of the first coil and the center of the second coil. But again, the ratio of radii, ratio of number of turns, ratio of something else. What is that something else? Currents and number of turns and what else is this? Radii, currents, and number of turns. Three parameters ratios are given for two coils, and we are asked to find the magnetic fields at the centers of these two coils. Ratio. So we have one coil having radius R1, another coil of radius R2, right? It is having n1 number of turns, it is having n2 number of turns. So find the magnetic field, and this current I1 is flowing, and in this current I2 is flowing. So we have to find magnetic fields at the centers. Stop it, man. So we have to find what is the magnetic field ratio V1 by V2. So B U at the center of a circular coil is what? What is the formula for magnetic field at the center of a circular coil? V naught I by 2R. V naught I by 2r. Mu naught I by 4 pi r into theta. Theta for complete circle is 2 pi. So 2 pi gets cancelled and here we get 2. So mu naught. So you know B is equal to mu naught I by 2r at the center of the circle. So it is a constant. So you can say B is proportional to I by R for one turn. For n turns, n into mu naught I by R. So you can say it is proportional to n I by R. So the first one, you can take it as B1 by B2 is equal to N1 I1 by R1. For second one, N2 I2 by R2. So this you can rewrite it as, because of this, B1 by B2 is equal to what? N1 by N2 into R2 by R1. Or you can say it first, I1 by I2 into R2 by R1. Reciprocal, reverse of. So take this value, direct substitution on the right. Yes, what is the answer? Then do it. Finished? Right. Okay. So fine. Four into zero value from 0 is 4 pi is 3,000. Mu naught value is 4 pi into 10 to the power minus. Otherwise, if you take by 4 pi, get 10. Okay. Yes. Right. So can you do some few more questions? Time up. Hmm. Hmm. Okay then. Okay, I'm winding up. Okay, you guys practice all remaining questions based on these two concepts. Then we'll discuss what is the magnetic field on the axial point of circle coil in the next session. And one more application is there as part of what is this Biot-Savart law? That is how to find magnetic field due to solenoid by using solenoid. What is the solenoid and how it looks like? How to find that? That we'll see in the next class. Fine? Yes. Okay then. Practice and come.